The rotation curve of a disk galaxy is a plot of the measured magnitude of the orbital velocities of visible stars or gas in that galaxy versus their radial distance from that galaxy's center, and typically rendered graphically as a plot. The measured rotation rates of those stars do not match the calculated rates, which calculation is based on well-known laws of physics. A general feature of the galaxy rotation curves is that the orbital speed of stars and gas rises or is almost constant as far from the galactic center as it can be measured. That is, stars are observed to revolve around the center of the galaxy at increasing or the same speed over a large range of distances from the center of the galaxy. Given the observed mass distributions in galaxies, the orbital speed should decline at increasing distances in the same way as do other systems with most of their mass in the center, such as the Solar System or the moons of Jupiter. The rotation curves of spiral galaxies are also known to be asymmetric. The observational data from each side of a galaxy are generally averaged. Rotation curve asymmetry appears to be normal rather than exceptional. The galaxy rotation problem is the discrepancy between observed galaxy rotation curves and the theoretical prediction, assuming a centrally dominated mass associated with the observed luminous material. When mass profiles of galaxies are calculated from the distribution of stars in spirals and mass-to-light ratios in the stellar disks, they do not match with the masses derived from the observed rotation curves and the law of gravity. A solution to this conundrum is to hypothesize the existence of dark matter and to assume its distribution from the galaxy's center out to its halo. Though dark matter is by far the most accepted explanation of the rotation problem, other proposals have been offered with varying degrees of success. Of the possible alternatives, the most notable is modified Newtonian dynamics, which involves modifying the laws of gravity. History and description of the galaxy rotation problem. In 1932, Jan Hendrik Oort became the first to report that measurements of the stars in the solar neighborhood moved faster than expected when a mass distribution based upon visible matter was assumed. But this measurement was later determined to be essentially erroneous. In 1939, Horace Babcock reported in his PhD thesis measurements of the rotation curve for Andromeda, which suggested that the mass-to-luminosity ratio increases radially. He attributed that to either the absorption of light within the galaxy or to modified dynamics in the outer portions of the spiral and not to any form of missing matter. In 1959, Luis Volders demonstrated that spiral galaxy M33 does not spin as expected according to Keplerian dynamics. In the late 1960s and early 1970s, Vera Rubin, an astronomer at the Department of Terrestrial Magnetism at the Carnegie Institution of Washington, worked with a new sensitive spectrograph that could measure the velocity curve of edge-on spiral galaxies to a greater degree of accuracy than had ever before been achieved. Together with fellow staff member Kent Ford, Rubin announced at a 1975 meeting of the American Astronomical Society the discovery that most stars in spiral galaxies orbit at roughly the same speed, and that this implied that galaxy masses grow approximately linearly with radius well beyond the location of most of the stars. Rubin presented her results in an influential paper in 1980. These were the first robust results to suggest that either Newtonian gravity does not apply universally or that, conservatively, upwards of 50% of the mass of galaxies was contained in the relatively dark galactic halo. Although initially met with skepticism, Rubin's results have been confirmed over the subsequent decades. If Newtonian mechanics is assumed to be correct, it would follow that most of the mass of the galaxy had to be in the galactic bulge near the center, and that the stars and gas in the disk portion should orbit the center at decreasing velocities with radial distance from the galactic center. Observations of the rotation curve of spirals, however, do not bear this out. Rather, the curves do not decrease in the expected inverse square root relationship but are flat, i.e., outside of the central bulge the speed is nearly a constant. It is also observed that galaxies with a uniform distribution of luminous matter have a rotation curve that rises from the center to the edge, and most low-surface brightness galaxies have the same anomalous rotation curve. The rotation curves might be explained by hypothesizing the existence of a substantial amount of matter permeating the galaxy that is not emitting light in the mass-to-light ratio of the central bulge. The material responsible for the extra mass was dubbed dark matter, the existence of which was first posited in the 1930s by Jan Oort in his measurements of the Oort constants and Fritz Zwicky in his studies of the masses of galaxy clusters. The existence of non-baryonic cold dark matter is today a major feature of the lambda-CDM model that describes the cosmology of the universe. Halo density profiles. In order to accommodate a flat rotation curve, a density profile for a galaxy and its environs must be different than one that is centrally concentrated. Newton's version of Kepler's third law states that the radial density profile ρ is, where v is the radial orbital velocity profile and g is the gravitational constant. This profile closely matches the expectations of a singular isothermal sphere profile where if v is approximately constant then the density ρr-2 to some inner core radius, where the density is then assumed constant. Observations do not comport with such a simple profile, as reported by Navarro, Frank, and White in a seminal 1996 paper. The authors then remarked that a gently changing logarithmic slope for a density profile function could also accommodate approximately flat rotation curves over large scales. They found the famous Navarro-Frank-White profile, which is consistent both with n-body simulations and observations given by where the central density ρ0 and the scale radius rs are parameters that vary from halo to halo. Because the slope of the density profile diverges at the center, other alternative profiles have been proposed. For example, the Inisto profile, which has exhibited better agreement with certain dark matter halo simulations. Observations of orbit velocities in spiral galaxies suggest a mass structure according to, with phi the galaxy gravitational potential. Since observations of galaxy rotation do not match the distribution expected from application of Kepler's laws, they do not match the distribution of luminous matter. This implies that spiral galaxies contain large amounts of dark matter or, in alternative, the existence of exotic physics in action on galactic scales. Cosmology tells us that about 84% of the mass of the universe is composed of dark matter, a massive component which does not emit radiation, but it dominates the gravitational potential of galaxies and cluster of galaxies. Galaxies are baryonic condensations of stars and gas that lie at the centers of much larger dark halos of dark matter, affected by a gravitational instability caused by primordial density fluctuations. The main goal has become to understand the nature and the history of these ubiquitous dark halos by investigating the properties of the galaxies they contain. The measurement of the kinematics of the observable stars and gas has become a tool to investigate the nature of dark matter, as to its content and distribution relative to that of the various baryonic components of those galaxies. Further investigations. The rotational dynamics of galaxies are well characterized by their position on the Tully-Fisher relation, which shows that for spiral galaxies the rotational velocity is uniquely related to its total luminosity. A consistent way to predict the rotational velocity of a spiral galaxy is to measure its bolometric luminosity and then read its rotation rate from its location on the Tully-Fisher diagram. Conversely, knowing the rotational velocity of a spiral galaxy gives its luminosity. Thus, the magnitude of the galaxy rotation is related to the galaxy's visible mass. While precise fitting bulge, disk, and halo density profiles is a rather complicated process, It is straightforward to model the observables of rotating galaxies through this relationship. So, while state-of-the-art cosmological and galaxy formation simulations of dark matter with normal baryonic matter included can be matched to galaxy observations, there is not yet any straightforward explanation as to why the observed scaling relationship exists. Additionally, detailed investigations of the rotation curves of low-surface brightness galaxies in the 1990s and of their position on the Tully-Fisher relation showed that LSB galaxies had to have dark matter halos that are more extended and less dense than those of HSB galaxies, and thus surface brightness is related to the halo properties. Such dark matter-dominated dwarf galaxies may hold the key to solving the dwarf galaxy problem of structure or formation. Very importantly, the analysis of the inner parts of low and high surface brightness galaxies showed that the shape of the rotation curves in the center of dark matter-dominated systems indicated a profile that differed from the NFW spatial mass distribution profile. This so-called cusp-I halo problem is a persistent problem for the standard cold dark matter theory. Simulations involving the feedback of stellar energy into the interstellar medium in order to alter the predicted dark matter distribution in the innermost regions of galaxies are frequently invoked in this context. Alternatives to dark matter. There have been a number of attempts to solve the problem of galaxy rotation by modifying gravity without invoking dark matter. One of the most discussed is modified Newtonian dynamics, originally proposed by Mordechai Milgram in 1983, which modifies the Newtonian force law at low accelerations to enhance the effective gravitational attraction. Mond has had a considerable amount of success in predicting the rotation curves of low-surface brightness galaxies, matching the baryonic Tully-Fisher relation, and the velocity dispersions of the small satellite galaxies of the local group. These results are surprising in the context of dark matter, which does not make the same predictions as Mond without considerable fine-tuning. Mond is not a relativistic theory, although relativistic theories which reduce to Mond have been proposed, such as tensor vector scalar gravity, scalar tensor vector gravity, and the theory of Capozziello and De Laurentiis. Bibliography. V. Rubin. K. Ford, Jr. Rotation of the Andromeda Nebula from a Spectroscopic Survey of Emission Regions. Astrophysical Journal 159. 379. Bibcode 1970 APJ 159 379 R. DOI 10.1086 150317. This was the first detailed study of orbital rotation in galaxies. V. Rubin. Thonard. K. Ford, Jr. Rotational properties of 21 SC galaxies with a large range of luminosities and radii from NGC 4605 to UGC 2885. Astrophysical Journal 238. 471. Bibcode 1980 APJ 238 471 R. DOI 10.1086 158003. Observations of a set of spiral galaxies gave convincing evidence that orbital velocities of stars in galaxies were unexpectedly high at large distances from the nucleus. This paper was influential in convincing astronomers that most of the matter in the universe is dark, and much of it is clumped about galaxies. Galactic Astronomy, Dimitri Miles and Paul McRae, W. H. Freeman 1968.